Hi, this video will cover section 3.1, exponential functions and their graphs. So the objectives of this section will be to recognize and evaluate exponential functions with base a. Here a is just a real number. Also, we will be graphing exponential functions and use the one-to-one property. We will learn to recognize, evaluate, and graph exponential functions with base e. E is a number, but not like a, which is representing just a real number. E actually has an approximation, so we will be discussing that. And then we will use some exponential functions to model and solve some real life problems, as we usually do on every section. Okay, so so far this text has dealt mainly with algebraic functions, which include polynomial functions that we study in chapter 2, and also rational functions. So those are the ones that we or the book is considering as algebraic: polynomial and rational. Remember, rational was the ratio of two polynomials. So in this chapter 3, which by the way has 5 sections, so we are going to have a test pretty soon, you will study 2 types of non-algebraic functions, and those 2 are exponential functions and logarithmic functions. So these functions, we refer to them as transcendental functions. And I actually like to teach this chapter because it's very applicable to things that happen in life, and there are several equations or properties that are needed and used in several fields of science, including computer science, statistics. You see a lot of this in economics even. And yeah, so we will cover some questions. What else can I tell you? And forensics, population growth. So, I mean, the examples are more like meaningful, and that's one of the reasons I like to teach it. So, an exponential function is going to have, a simple one, parent function, will have a base, which is the letter A. That will be the base. And that base needs to be greater than 0. And then we will have an exponent, and that exponent will be the independent variable, which will be x. So this will be the exponent, and that x is the independent variable. Now, we also need to point out that the base cannot equal to a 1, and I will show you why in a minute. So the base must be positive and also does not equal one. And the reason for that is that if you had an exponential function with a base of 1, you will have something that, if we construct a table, and remember f of x is your output, your y value. So if we had 1 to the power 2, 1 to the power 3, 1 to the power 0, for all of those, in fact, I shouldn't do that. The x value will be like, let's say 1, 2, 3, 0. And so for the substitution, it will be 1 to the power 1, 1 to the power 2, 1 to the power 3, because the equation is 1 to the power x, and then 1 to the power 0. So for all of these values, we will always get a 1. And so it would still be a function. It will just happen to be a constant function where the only y value occurs at 1. So if the x is 0, the y value is 1. If x is 1, the y value is 1. And that will be the case for all the other x values. The y value will always be 1, and that will just make a horizontal line with the equation y is equal to 1, because 1 to any power is always going to be equal to 1. So that's why we take that out of the options for the base of an exponential function. And now the exponent here, which is x, the independent variable, so the set of all those values, we call that the domain, is going to be all real numbers. You could have a positive exponent, negative exponent, a zero exponent, but we'll discuss that later. So what we're going to do now, and I'm just going to write here how you perhaps will enter it on your calculator. So if you have to evaluate something, like this function 2 to the power x. So if you have to evaluate f of, and they're giving us an x value here, negative 3.1. So what that means is that you make your exponent a negative 3.1. So when you enter something like this on your calculator, of course you enter your base first, and then you may see a key that looks like that, and some people call it caret. And then you have to enter a number so that you enter the exponent. Now, what happens here is that you need a negative sign, as you could see here. And so that negative, there's a button on your calculator, and it's kind of like at the bottom. I think it's below number 9. And it has a negative sign, like a little one, and then it has parentheses around it. And so that key is the one that you need to put when you enter a negative quantity in the front, or a negative symbol, I should say. Then, of course, you enter your number 3.1, and then you press enter. So, that will be a way to enter something like that. And maybe you want to make sure that you put parentheses around the 3.1, the negative 3.1. And here, this negative, it doesn't mean that you put extra parentheses. It's just how the calculator key looks like. So I'll just put a little negative. So that's how you will enter that. And then for the next question, you have a negative sign here. So that will also be important to notice. It will be the same button that has the negative sign inside parentheses, and I believe is below number 9. Actually, I'm gonna check. Okay, so I checked with the keyboard of a calculator, and it's below number 3. That's the sign that it's called negative. The other sign that we call minus, that is next to the plus sign. So your calculator should have 2. Okay, so if we enter that, actually I'm going to type in or write the answer for part A. 2 to the power negative 3.1. I'm just going to round 4 decimals, so it will be 0.1166. Okay, now the next question here, it will be 2 to the power negative pi. And so what I would suggest is that you locate the pi button on your calculator, because WebAssign is not going to want you to enter something with an approximation for pi. So it will be 2 exponent, and then again the same key with the negative sign. and then the button, the key or button that has the pi symbol. Okay, so that one, no, I forgot to enter exponent. Okay, so I hope you are practicing, because you're gonna have to enter things like this on your calculator. So rounded to 4 decimals, that's what I get. And then finally here we will enter 0.6, then the caret symbol. And then here for x, we have a fraction. Here I'm going to strongly recommend that you enter parentheses. So opening parentheses, and then 3, and then the division key, and then the 2, and then the key with the closing parentheses. It's very, very important that you keep parentheses around a fraction so that the whole thing is part of the exponent. And so that should be is going to be equal to 0.7114 if we round to 4 decimals after the decimal point. And yes, this is the answer for part C. And this is the answer for part B. Okay, so let's move on. And what we're going to do next is we're going to graph in the same coordinate plane. We're going to graph 2 to the power x, and then we're going to graph 4 to the power x. And so what we're going to do is just construct a table. It is pretty simple. So we're going to construct a table for 2 to the power x. So here we'll have our x values, and I would like for you to have negative 3, negative 2, negative 1, 0, 1, 2, and then 3. Let's add one more here. Okay. All right, so here we will have our function, which is f of x, which is the same as the y value. And so our base is 2. So what we're going to be doing is substituting our base. Well, our base will be constant. It will just be 2. What we're going to be changing will be the exponent with the x values that we have listed here. Now from there, we're going to get some points that will come from the xy value. So let's do this. So we have 2 to the power negative 3. In this case, there is a rule with exponents that if you have a negative exponent, you could use the inverse of this number, and then the exponent will remain with the 2, but it will be positive because you are switching it from being in the numerator, from being the exponent of the numerator to being the exponent of the denominator. So that's the rule we will use here, and that will give us 1 over 2 to the power 3. So 2 to the power 3 is 8. It's 2 times 2 times 2, that's 8. So this is 1 over 8. Okay, next one, it will be 2 to the power negative 2. So it's 1 over 2 squared. Actually, I'm going to zoom in a little bit. And that will be 1 over 2 squared, which is 4. Okay, next will be 2 to the power negative 1. So that will be 1 over 2 to the power 1, which is just 1/2. And then we'll have 2 to the power 0, which is equal to 1. Any number raised to the power 0 or expression raised to the power 0 is equal to 1, except for the number 0. 0 to the power 0 is undefined. So any number except 0. And then 2 to the power 1 is just 2. The next ones are a lot easier. 2 to the power 2 is 2 squared, so 2 times 2, 4. And then 2 to the power 3, which will be 2 times 2 times 2, so that's 8. So from here, we're going to go ahead and graph our points. And what I'm going to do, let's just write the points. So we'll write them here. So I'm just going to write them here. -3, 1, 8. And then we're going to plot -2, 1, 4. If you see, they're just coming from the table, so this is not necessary. I just want you to make sure you know where the points are coming from. Then we have 0, 1. Then we have 1, 2. And then 2, 4. And 3, 8. So what I'd like to do is to get started with the easiest, which will be the y-intercept here at 0, 1. So let's just zoom a little bit right there. But that's perfect. So we'll plot that point 0, 1. And then we'll plot 1, 2. So 1 for x, 2 for y. And then we're going to plot 2, 4. And 3, 8. Okay, and then we will also go on the now let's go ahead and graph the ones here on the first row. So -1, 1/2, -1, -2, 1/4, -3, 1/8. And so with those points, I'm going to go ahead and connect them. And don't make a straight line. They're supposed to be curvy. And what's happening here, of course, is not a very good graph. Actually, I'm going to trace it again. Let's do it. We could do better. Okay. There we go. That looks a lot better. And so that will be the graph of 2 to the x. Y equals 2 to the power x. I want to point out quickly that we will have a horizontal asymptote right here. And it will be on the x-axis, otherwise known as, let me write it here. So HA for horizontal asymptote is the equation y equals 0 because all the y's are equal to 0 on this line here. That's not part of the graph. It is the horizontal asymptote. And if you don't know what that is, you should watch video 2.6. Okay, and let's just write quickly the domain. It's all real numbers, so from -infinity to +infinity. And for the range, for this function, it's going to be the smallest value will be 0. However, 0 is not included, and that's why it's an asymptote. So we use parentheses to denote that 0 is not included, and then it goes up to infinity. Okay, now we're going to graph the other one, 4 to the power x. So let's go ahead and do the table for it. Okay, so we have x here, and here let's just start at -2. That will still be hard to graph, but okay. -1, 0, 1, 2. Okay. So if we find, and now our graph for g of x, it's 4 to the power x, so we will still be substituting here with where the x is, but now the base has changed to 4. So 4 to the power negative 2 is going to be 1 over 4 to the power positive 2. I actually need to zoom in here. Okay, so this was 1 over 4 square, and that will be 1 over 16. Then 4 to the power negative 1 is equal to 1 over 4 to the power 1, so that was 1/4. Here we have 4 to the power 0, so this is equal to 1. And then we have 4 to the power 1, that is equal to 16. 4 to the power 2, which is, I'm so sorry, this should be 4. 4 squared, it will be 16. And then, I mean, I can keep going. I can compute all of this. In fact, I could find like what is the value at 3.1, just like we did on the other example. And of course, I will just have to put it on the calculator, you know, but it is still doable. We could still find it. We could still find what is, let's say that we say 1/2. So remember, the domain is all real numbers. The domain is the x value. So we will be finding 4 to the power 1/2. And that is the x value. So it's okay to use that. We don't have to only use integers. And so that will actually be the square root of 4, which is 2. So that's another good point that we could be graphing. And so let's do that. And just so you know exactly what I am going to be plotting, it will be the points, -2, 1 over 16, -1 over 1/4, 0, 1, 1, 4. And then here I'm going to have 2, 16. I'll get creative with it. And then let's see, 1/2 for the x. And then we got a 2 for that one. So that would be a good point, a good reference point. Okay, so let's go ahead and do this. Okay, so we have, well, let's start with the positive ones. Let's start with the second row. So let's start here. 1/2, 2, somewhere here. And then let's start right here. 0, 1 with the y-intercept. Okay, then 1, 4. And then 2, 16. Now that one is out of the range here, but maybe we could find it. If here's 10, we will have 1, 2, 3, 4, 5, 6. Oh, but then we need to go 4 in this direction. 1, 2, 3, 4. Well, so it could be like right here. All right, and then let's graph the ones with the negative x. So -1, 1/4. So -1, 1/4. So it's like 1/2 of a half, like right there. And then this one here is pretty hard to graph and get a precise, you know, point. But, you know, as long as you do not touch the x-axis, that's okay. Because remember, the x-axis is representing the horizontal asymptote. So, okay, and then here, same thing. We're not touching the x-axis. Okay, I'm going to try to graph this again. Okay, and so not the best graphing here. So, but I wanted to show you how you can actually find them. Okay, so, and I really don't like what's happening here, how like one is crossing with the other, because that's just not how it happens. Okay, and then we can do better. And in fact, if I was to keep going, you could see how the graph in purple, which is representing the function for y equals 4 to the power x, you could see how the function in purple, 4 to the power x, is growing faster. When they have the same x value of 1, 2 to the x is equal to 2, and 4 to the x is equal to 4. More evident when x is equal to 2. 2 to the power 2 is 4, and 4 to the power 2 is 16. Now, if I was to include, I didn't want to do that because I knew I didn't have time, space for it, but, oh, I'm erasing everything now. Okay, so actually, if I change that exponent to a 3 and I calculate 4 to the power 3 is 64. So, you know, here it becomes more evident that if they have the same x value of 3, the function with the base of 2, it is way smaller. It's 2 to the power 3 is 8 because the base is 2. But if you change the base by 4 and then you have the same x value, it will be 4 to the power 3, which is 64. And you could see the difference between 64 and 8. It's pretty big. And if we were to try to keep graphing them, you could see how the difference will be pretty evident. So I do have the two graphs graphed on Desmos here, and you could see the graph in red is 2 to the power x, so you could see we got the same points. The y-intercept is at 1, 0, and then we have 2, 1, 4, and so on. So 3, 8 right here. So if I graph the one in blue, and I'm actually going to zoom out a little bit so you can see better. And then now I'm going to graph, oops, oh, what did I do? Okay, here we go. I'm going to go ahead and graph the one in blue, which is 4 to the power x. And you can see that they both have the same y-intercept here at the point 0, 1. And then, however, right after that, the graph of 4 to the power x, which is the one in blue, it starts growing faster or increasing faster. And if I keep zooming out or try to show you, you could see how it is more and more like the gap gets bigger of how much one is increasing rather than the other. You could see there the value is 7.168, and for that y value, the other one was like about 3.58. So that base is something that scientists actually use when they are determining the spread of a virus. And a very good example is, uh, let's just imagine like zombies. So if one person turns into a zombie, they can potentially make two zombies, and then those two make another two. So that will be four. And then after that, you could get, out of all those zombies, you could get eight. And that's the idea of the spread of a virus, also the spread of a rumor, that it is exponential. And of course, there's no secret that COVID-19 is the same way. One of the things that keeps a lot of us up at night. And yeah, I mean, a different, depending on the base and also of other numbers that will be included in the equation or the model, the exponential model, depending on those, that implies how fast a graph can increase. Now, it's probably worth mentioning that if we have, if we remember our arrow notation, we have here that the x-axis is the horizontal asymptote, because as x, let me see. Okay, as x gets smaller, as you can see here, the graph starts leveling. Actually, I'm going to make this a little thicker right here, and it starts getting smaller and smaller. Or I should say, because this is x approaching negative infinity, right? X is getting more and more negative, or getting smaller. Remember, the arrow means that. And as you can see, as x approaches positive infinity, as x gets larger and larger, the graph keeps growing and growing and growing exponentially. So we say that the function a of x approaches infinity. And so, that is just how exponential functions work. If I show you, let's go back to Desmos, and I want to show you the table. Let's look at the table. And so if we look at the, for example, x to the power, well, actually, I have a keyboard here, x to the power 2 to the power 100, maybe too big. Okay, let's try 10, 2 to the power 10. And then if we try to get the table here for 4 to the power x, and we enter 100, you see the number, oh no, we say we were just going to use 10. There we go. It's still pretty big. I don't feel like teaching you scientific notation right now. But yeah, let's try 8. So we were getting an answer in scientific notation, so we were going to have to multiply by 10, move the decimal point. So you can see here the difference between 2 to the x. When x is 8, it will be 256. For 4 to the x, when x is 8, it is 65,536. You could compare this to how COVID-19 has spread in different countries. So we already mentioned domain is all real numbers. The exponent could be any real number. The range, because we have that horizontal asymptote. Oh, right here. Horizontal asymptote at the line y equals 0, or the x-axis. That's why for our range, we select from 0 to infinity, but we do not include 0, so we use regular parentheses. And then remember, for infinity and negative infinity, we always use parentheses. We have the y-intercept right here. And we could also say that the graph is increasing. And we call this behavior exponential growth. Increasing. And the graph is obviously continuous. We have no gaps there. Also, it's important to notice here that we are claiming that the base is greater than 1, just like the ones that we graphed here. Base 2, base 4. Now, if we change that base to something, well, okay, we're still claiming it's bigger than 1, but we change the exponent to negative, then the graph is going to be a reflection of the previous one. Remember, if you change the negatives to negative, let's pick a point here. So let's say that we have, here 2, 4. And so if we reflect that point across, if we change the x to -2, then the point will be reflected across the y-axis. So it will become -2, 4. And then we will have, if we do that with all the points, we will have a function that will be decreasing. So if we do that with the exponent, make it negative, it will be a reflection of that. So that's the one we have on the next slide. I just want to make sure I take this out. Okay, and let's go here. So if we make that exponent negative, we will have that reflection. This graph is said to be decreasing, and we refer to this behavior as exponential decay. Okay, so if we have the same y-intercept, you could see it here, 0, 1. We have the exact same horizontal asymptote right here. That will be the x-axis, the horizontal asymptote, or the line y equals 0. And that is because you could see that as x gets larger in this case, as we move x in this direction, the graph is going to get closer and closer to the x-axis, but it's not going to touch it. And so we say that the function approaches 0. That's why it is the horizontal asymptote. The graph is obviously continuous, no gaps or open circles in between. And we have the domain is also all real numbers. And the range is the same as the previous one because the smallest value is 0 without including 0. That's why we use parentheses and, of course, infinity. However, it is decreasing. So now for this one, we will say something like as x gets smaller, so as x goes to negative infinity, the function, or a to the negative x, goes to infinity. But that is not determining the horizontal asymptote. That will be determined from what's happening on this side of the graph as the x gets larger, because it is decreasing in this case. All right, so I want to show you something before we move on. And so we're going to take this graph out. So I'm going to graph it again. And what I also want to graph is 2 to the power negative. Okay, no. Okay, there we go. So I need the standard view. So I'm just trying to zoom in. Okay. There we go. That's perfect. So let's just show the first one that we already graphed, 2 to the power x. And you could see we have some points there that are in red, and you could see the coordinates because they're on the table as well. Okay, and so what we're going to do is graph the 2 to the power negative x. So we know it should be a reflection across the y-axis, so it will look like that. And this is what I was talking about. We have the point 1 comma 2, but we also have this point reflected negative 1 comma 2. And for this point here, 2 comma 4, we have the point reflected. Just need to. There you go, negative 2 comma 4. So that is how the graph will look, decreasing, right, compared to the other. But there is another way to get the same graph, the one that is decreasing. And I need to get this one out. Okay, so that's 2 to the x. That's 2 to the negative x. No, the other way. That is 2 to the x. And that is 2 to the negative x. So it's decreasing. So I want you to notice what I'm going to type. I'm going to have y equals, and then as the base, I'm going to enter 1 over 2 as a fraction. Close the parentheses. Okay, that was probably unnecessary. I'm just going to use the arrow to get out of the parentheses. And then I'm going to use the a to the power b to use the exponent symbol here and then put an x there. And so as you can see, the two graphs are overlapping. So there's the 2 to the power negative x by itself. And then I'm going to graph 1/2 to the power x. So these two graphs are the same thing. That's just 1/2 to the power x. And then if I graph 2 to the power negative x, it will be there. You cannot see anything else because they're the same, they're overlapping. So that is also important to know that if you have a positive exponent, but your base is less than 1, you will also see that decreasing behavior. That is so important. So we could get something similar if a is less than 1, and let's call it bigger than 0. And then x is positive. So if you had something like any number between 0 and 1 without including 0 and 1, remember? So let's say you had like 1/4 or 0.25. 0.25 is inside that interval between 0 and 1. And so that, if we were to graph something like that, 0.25 to the power x, that will be the same as 1/4 to the power x. And that will actually be the same thing as 4 to the power negative x. Yes, so for all of those, it will also be decreasing and it will fit the same properties as the ones that we did on this slide with the power negative x. Okay, now we're going to look at some properties that will help us get to the point where we could solve equations. So one of those properties is the one-to-one property. And so it's pretty obvious that if you, with the graphs that we just did, if you perform the horizontal line test to test for the one-to-one property, it will pass it because it will only touch the graph at one point. Um, so that property allows us to derive others, such as if you're comparing two the same base with two different exponents, but if you're saying that they are equal, then you are also saying that the exponents are equal, because if the bases are equal and they're raised to an exponent, so then the exponents must be equal. And of course, we use the same constraints for the base. It needs to be greater than 0 and it cannot equal to 1. So let me give you an example. So if we have 5 to the power 2, and then here I have 5 to the power x, I know that 5 is equal to 5. So therefore, 2 must be equal to x, the two exponents. So it is that simple to use. The hardest part is to get us to convert some random number to something that will be of the same base, because you must have the same base before you can use this property. So let me actually give you some examples from the textbook. Okay, so I found some examples on your textbook. So let's solve them. So the first one here, 9 equals 3 to the power x plus 1. What I need to do is change this number 9 so that it's also written with a base of 3. So 3 to the power 2, that will give us the exact same thing as 3 to the power x plus 1. And so now that we see that our bases are equal on both sides, we can create a new equation that will just come from the exponents. 2 equals x plus 1, because we're saying is 3 equals to 3? Yes. So 2 must equal x plus 1. So then we create a linear equation, 2 equals x plus 1. And this will turn into x is equal to 2 minus 1, which will be x is equal to 1. And that is the answer. Now let's do the one on the left. The number 8 cannot be turned into, how do we call it? Something of base 1/2 that easily, but if you think about it, yes, you could. Because, in fact, let's do it the other way. If we turn, actually, I'm going to just move this quickly. Okay, so we have it there. Oh no, what did I do? Okay, so back here, I think it was something like that. Yes. So that's our equation, and what I am going to do is use that property that says I can move my 2 to the numerator, and now the exponent, instead of being positive, it's going to be negative. So 2 to the negative x equals, now the number 8 is going to be 2 to the power third, because, to the power 3, because 2 times 2 times 2 is equal to 8. So I force this 2 to be with the same base, which is 2. Now that we can confirm that 2 is equal to 2, then we can say the exponents must be equal as well. So negative x is equal to 3. So that means that x is equal to negative 3, like that. And that is how you use it. If you need I believe we do have a live session this week. I'm going to check quickly. We do have a live session this week, so we could do more problems. Definitely more of the complicated problems because, of course, these two are not as difficult. Okay, so this PowerPoint is actually skipping transformations with exponential functions. So I'm going to give you some quick, I'm going to show you some quick examples. So let's go ahead and just use that parent function that we have from the beginning, 2 to the power x. Let's graph it, and you could see that if we start doing things to it, for example, say y equals 2 to the power x, and then we add a 1 like that, it will be doing a vertical shift of 1 unit up. Now, for example, if we do things like y equals 2 to the power x, and then we say minus 2, that will be a shift of down 2 units down. You could see that there from the parent function. And of course, we could also have horizontal shifts. So what I'm going to do, let me go ahead and type them. So let's say 2 to the power. Now, what I'm going to do is actually put the exponent in parentheses, and I'm going to say x minus 3. And so you could see the parent function. Let me switch the color of this one so it's more evident. Okay, so the parent function is still in blue. That's the parent function in blue. And then the one that I have here is going to be a shift of 3 units to the right. Remember, the horizontal shifting is counterintuitive. And so that's what we get. So if I show you that, you could see how the y-intercept is going to be shifted 3 units to the right, and it's going to be here at that point. So there you can see it. Now, if I want to shift that to the left instead, I'm going to go ahead here and just change that sign to a positive, and then you can see how it's shifted to the left, the one in red. Let's say we would just want to shift it 1 unit, so we could do that. And then we could also have combined shiftings here. We could do a quick shift of, let's say, 2 units down. So that's the graph in red. The blue is the parent function the whole time. I can show you here. And of course, if you do a vertical shift, the horizontal asymptote will change with it. Oh no, what did I do? It will change with it. Okay, so now you could see we could have a combined vertical and horizontal shift. Let's just quickly do an example of a shift across the x-axis. So if we want to cross the x-axis, we change the outputs to their opposite. So in other words, we change the y value. So we will put a negative in front of it, then the same base, then x. And that, you could see that will be a reflection. The one in blue is the parent function 2 to the x. The one in green is the reflection across the x-axis. Now, if we want to have a reflection across the y-axis, then it will be, the negative will be within the exponent like that. And let me get rid of this one in green. So blue is parent function, purple is reflection across the y-axis. So you could see here how they will look. The one in green is the reflection across the x-axis. And of course, keep in mind that you can have reflections combined with, how should we call this, shiftings, vertical and horizontal shiftings. Okay, so that's enough for graphs. Let's move on to the next concept here, which is the natural base E. the number e, which is approximately 2.71, a2, a1, a2, a1, and it is the second most famous irrational number. And I say the second most famous because the most famous is pi. The second most famous irrational number. And so we refer to it is commonly used, and not just in this class, math, but also in many fields. And again, I go with computer science, statistics, economics, chemistry, biology, forensic science. So it's used so much that it has its own key on the calculator. And it is towards, actually, I'm going to look at the board. It's on the left side, kind of like towards the middle. And you will see it as an e to the power x. Or maybe you do have a calculator that says ln, and then with a different color, you have an e to the power x, like that. So either one of those. And whenever you use it for this class, I will suggest that you only use the button for E, okay? Do not try to enter the approximation because you know how picky WebAssign is, and you don't want to round too soon and get the wrong answer. So this number appears in nature and in certain patterns, and so because of that, it's called the natural base. And our next section, which is 3.2, which is logarithms, we look at certain logarithms based on their base. And we have a special one, which is logarithm base e, and we actually call it natural log or logarithm. I'll just use log for simplicity right now. So yeah, and so the function e to the power x, we refer to it as the natural exponential function. And we are going to use all the properties that we learn with exponentials and logarithms and logarithmic functions. We will be applying them with the base e, or with the natural log, which is the topic of our next section. So here is the graph, as you can see it here, just so you can get an idea how it will look with the other ones. I have so many graphs here now. So let's get rid of this 2 first. I'm going to adjust the video window. Okay, and so let's go ahead and graph. I hope this will recognize it. Yes, it is recognizing it. That, as you can see here, it's thinking that I'm going to graph just a horizontal line. In fact, it's right here at 2.782. But I want to graph an exponential, so I need the power x. And you can see it right there. I'm going to just graph one more, which was the 4 to the power x, just so you remember how they look like. So you could see the smallest base in this case will be the 2. Let's start with the biggest. So the biggest base was 4 to the x. That's the graph in red. Then if I graph 2 to the x, it will be there. And if I graph e to the power x, because e is approximately 2.71, it is a number between 2 and 4, bigger than 2, smaller than 4. So the graph is going to be less steep than 2 to the x. No, the other way. Less steep than 4 to the x, but steeper than 2 to the x. So let's see, and if I'm correct, the line should be right in the middle of the red and blue. And that's true. And you could see all of them have the same y-intercept. So that is the graph of e to the x. Okay, let's see. it is increasing if it's in that form. Now it says here to evaluate this with your calculator. Since we already graphed it on decimals, let's just go ahead and enter the x values and get them from there. So we're going to need -2, -1.25, and -0.03. So let's do that. Okay, so to get the table, I type the equation and then I'm gonna click on settings and then table. And then I can just enter the x values that I want. And we already have for x equals -2. So this is the y value that we're going to copy. So that's going to be 0.13. Let's round 4 digits. So it will be 53. Okay, so that we're done with the first. Then when x is -1, we look at the table. Here's -1, so we look at that y value, which is 0.3679 if we round 4 digits after the decimal point. So now the next one, we don't have it. However, we could always type it on decimals. So let's see, that will be the x value 0.25. And we get a y value here. So that's going to be 1.2840. Okay, and then finally, let's take the one for -0.3. So I'm going to be typing that here. So -0.03. And I am missing the point. I need to adjust this window. 0.3. There we go. And so for that particular x value, we have our y value here. So that will be 0.7408. And so those will be the answers for that example. Now, if you were evaluating this on your calculator, you might want to find that key that I was talking about. You might have to press the second key if, for example, you have a key that says ln, like in the TI-84, and then you will have here e to the power x. So you might have to press the second key to get the function in a different color as the key. So if that is the case, you will press second and then the ln key, so that on the screen it will print e to the power, and then it will open a little box here perhaps. And then in that little box, then you need if you don't see the little box open there in the place of the exponent, then you will have to use the caret symbol. Sometimes it does, the calculator does it on its own, kind of like it opens this. And then you just need to enter your x value or your exponent value, such as that. And remember that if it's a negative in the front, you need that key that has the little negative below number 3 on your keypad, because that's negative, not minus. Okay, so moving on, applications. One of the most familiar application, well, we're going to look at several others, but the most familiar example of exponential growth is an investment earning continuously compounded interest. And here for continuously, we will be using this formula for continuous compounding. But before we get to that one, and this is actually how bacteria grows, how population reproduces, what changes is the R. And so before we learn where that number comes from, in fact, it's also known as Euler's, actually, with capital E. In fact, I've been told it's pronounced Euler. Who knows? Euler's number or Euler's number. Because that is the French mathematician who derived it based on the concept that we see here of limits. And I know that you will learn this limits when you are in calculus, but we have been talking about how using arrow notation. So in this case, as this m, the independent variable that you see here and here, as that m increases, it goes to infinity. The function that you see here, the expression that you see here, that number that comes out of it, it gets, if we just turn it into a 2, it will be like 1 plus 1 to the power 1. So if m is equal to 1, this will be 1 plus 1 over 1. That's 1. So 1 plus 1 is 2. And then m is a 1. So let me just write it. 1 plus 1 over 1 to the power 1. So this will be equal to 2, and 2 to the power 1 is equal to 2. But then if we increase m to a 10, this m that goes here, and you type that on your calculator, you could see you get this number. And if you keep making that m larger and larger, you could see here the values being multiplied by 10. So here we have 1 million, 10 million. So as that x value, in fact not x but m, as m approaches infinity, the expression that comes from here, which is that function, we don't have a name for it here, so I'm gonna just rewriting. That expression is going to approach, I was gonna write infinity, sorry. It's going to approach the number e. It's gonna get closer and closer to the number e. So before we get into this concept, let's see a little bit about the backstory of it. And so for that, we're going to do an application that is very common. And that is the compound interest. So I don't really want to refer to this one as continuously, because the one that is continuously compounded is the one that I show you here. This is continuous, not the other one. In fact, let's just not consider this word here for now. Okay, so this is the formula, and let's go ahead and label each of the variables that we have here. So capital A is representing future value. And then we have capital P is representing principal, which is the money that you put in, or your initial value. Okay, and we have R for rate. So this is the rate, and it's going to be in decimal form. So if the rate is given to you in percent form, you have to convert it to decimal. And then also we have letter T that represents time. And this time, for problems about money, it is typically in years. And so if you are given a time in months, you have to convert it to a decimal or a fraction of the year. And then N, finally, is the number of compounding periods. Okay, so we do have places where we need N here and here, which is the number of compounded periods. So right there. Okay. And of course, as N increases without bound as it increases to infinity, like the table we saw before that. It was m was increasing to 10 million. Then that formula turns into the other, that will be the one for continuous compounding, which is the a equals p e to the power rt. So I want you to, when you take your exam, I want you to please, and even when you do your homework or your quizzes or whatever you need to do with these two formulas, I want you to make it very clear that they're not the same and that you will not use them interchangeably. The only time you will use this formula is if it says continuous. Please understand that. And you will use the other formula if your problem says something like, if n is equal to 1, it will be compounded annually. And this should be a double n, I believe. Like once a year. If n is equal to 2, it might say something like semi-annually or twice a year. I'm not really sure how to spell. I'm not sure if it's with a double N. Okay, if N is a 4, that means the compounding occurs 4 times per year. So then it will be quarterly, every 3 months. If N is equal to 6, it happens 6 times a year, so perhaps it's bi-monthly. No. Wrong, wrong, wrong. Is it? No, yes, it will be like a bi-monthly. No, because that would be twice in a month. Let's just say every 2 months. And if it says, let's say n equals 12, that will be because it happens monthly. And if it says n equals 52, that will be for weekly, if the compounding is weekly. And if it is n equals to, let's say, 365, it will be because the compounding happens daily. However, in real world problems, I mean, not in real world, but I mean, yes, but more real than in math class, the number that is used for n is 360, and that is because 360, it is a multiple of 12, of 6, of 4, of 2, and I believe also of 52. I could be wrong. Okay, so anyways, for this class, you will use 365 for daily as your n, unless you're required to use 360. Okay, so if we take that formula, what happens is that during the first year, if you were to compare a simple interest with a compound interest, simple interest, by the way, is a linear function. We looked at some problems in section 1.10. So that is simple interest, linear function, and a compound interest is an exponential function. However, for the first year only, they are equal. But the difference is that when you compound your interest, well, let's start with simple interest. Simple interest, you only earn interest from the principal, from the money that you put in there at the beginning, and that's it. With compound interest, you earn interest from the principal, but also from the interest that you accumulated from every compounding period. So your interest accumulated gets added to your principal, and that's how it is considered exponential. It grows way faster than simple interest. Okay, so if we take the formula for compound interest as we have here, and if we increase the, well, in fact, we let m equal n over r, meaning that n is equal to mr, as you could see here. And so we can see it here and here. So if we simplify this and we say that because you have r here and here, so that is equal to 1, so we could say like they cancel out. So then we have 1 over m here, and then here we have the mrt that was still from here. So if we simplify that by one of the laws with exponents, we can take that one, and if you are multiplying exponents, you could actually, if you are doing something like the power of a power, that's one of the properties. If you have like 3 square and then you have a 3 here, what you have to do is multiply the exponent, so it will be 3 to the power 6. Okay, so here we could also separate them and say 3 to the power 6, we could write it as 3 square and then raised to the power 3, if you go from right to left. So that's what we're doing here. We're taking the MRT, and we are going to take M and just leave it here, and then the RT are going to come out here. So they are similar, and we're just doing that for convenience because we want to get an expression that looks like this. All right, so if that is entered on the calculator as a function and you want to graph it, you could see that the greater the value of m, the closer it gets to the approximation for e. So I'm going to graph it. So right here you could see the graph, and red is just a horizontal line, and it's the equation y equals e to the power 1, which is approximately y equals 2.718. That's just a horizontal line. It is constant. And here the graph in black is the one that comes from here. Instead of m, I'm using x. And I just want to show you how, and if we increase the value for x, the graph is just going to align or get closer and closer and closer, not actually overlapping, but it will get closer and closer to the 0.718 or to the actual approximation. So let's go ahead and look at the and see if the graph that I have, it is actually, it has a gap in between, because yes, you could see x cannot be 0. Okay, so if I take the table of this graph, and as you saw before, if we enter big numbers, I don't know, 10, we get that. Okay, let's just use 10. Oh, I'm not using the correct graph. Okay, so I'm gonna enter a number like, let's say 1 or 1, And then and that's e to the 1. If I enter 10, I get that number. And if I enter 100, I get that number. So I am actually getting closer and closer to the number e. And actually, I'm going to try to expand this side. Okay, that's better. And see, we get closer to the number that we have here. Okay, so let's get back to our slide. And so if we want to do a problem that requires continuous compounding or compounding per year, you have to be very careful that when you enter things on your calculator, let's say that we have an example, the principal is equal to 100 and then the rate is equal to 4%. So you have to convert that to a decimal, multiplying or dividing by 100, or in other words, moving your decimal point 2 units to the left. And then you will need, let's imagine it says it happens weekly, so n will be 52. And then the time, let's imagine it says 3 years. So it will be just 3. So when you enter something like that on your calculator, it will be 100, you open parentheses, then you will have 1 plus, and then again parentheses for this fraction in here. So that will be the rate, which is 0.04 divided by 52, close parentheses, close again, exponent, and then in there you will enter 52 times 3 for years. So be very careful with those exponents. Now, if it was to say continuous compounding, then you will use this formula. So we do have an example here. Let's do it quickly. So we have an investment of $12,000. That is also a way to call the principal what you're investing at first. The annual rate was at 3%, so 0.03. And it says find the balance after 5 years, so t is equal to 5 when the interest is compounded, and we have different cases. So for A, quarterly, it implies n equals 4. For monthly, n equals 12. And for continuously, we use a completely different formula. A equals PE to the power RT. Okay, so monthly is 12. All right, so let's do part A, and the formula is this. Let me just write it here. A equals P parentheses 1 plus R over N parentheses NT. Okay, so on the first one, principal is 12,000. Then we have 1 plus, the rate is 0.03 divided by N. N in this case is going to be 4 for quarterly because we were doing part A. And then here, for the exponent, it's going to be 4 times t, which is the years, and the years is not 3 but 5. There we go. So that's for the years where t goes. And here is where n goes. And here is where r goes. Okay, then let's do our substitution for part B, and then we'll get all the answers. So for part B, we're going to have 12,000 again. 1 plus 0.03 divided. Now the compounding periods are 12 for monthly. So we put a 12 here, and then in the exponent 12 times the years, which is 5. So there you have it. And then for the very last one, we use a complete different formula because it says continuously. So in this case, it will be A is equal to 12,000 e to the power, the rate is 0.03 right here, times t, which is 5. And so you could pause the video, practice how to enter it on your calculator. So I got my answers, and for part A, I get 13,934 with, I went around to the nearest hundredth because we're talking about money, so for cents, and that would be with 21 cents. The next one will be 13,934. No, I'm sorry, not, oh, this is actually wrong. This should be 39. So that was 13,939 with, no, oh my gosh, 34 with 21 cents. For part B is 939, this is a 9, and then with 40 cents. Okay, that was for monthly, n equals 12. Now for continuously, that would be like a non-stop accumulating interest. So that will be 13,942 with 1 cent. And so as you could see, as the compounding period, the number of compounding periods increases, the output is also going to increase. We're imagining here that the number of compounding periods, it's going towards infinity. And so, oh, I think that was just for us to do the solution, but we already did all 3 of them here. So this is the end of the video.